Okay, let us begin. If M is an L structure, show that the theory of M is complete. Any ideas how to prove this? I think we have discussed this in the class. Just a recap of things. What is the meaning of a complete theory? Every sentence is decided, which means either given statement, given sentence theta is a logical consequence of theory of M, or negation is a logical consequence. So can you show that? That should be very easy. Yeah, because for a given structure, what is theory of M? So recall, theory of M is defined to be all those sentences such that they are true in M. Okay. The vacation period has taken over your brains. Yes. So try to get out of it. Yeah, we still have to go a long way. Okay. So what does that mean? Now let phi be any sentence. Then what will happen with phi? Either phi will be satisfied by M, or phi negation, or phi will not be satisfied by M, right? Then exactly one of M satisfies phi and M doesn't satisfy phi holds. Correct? Only one of it can hold. But what is the meaning of M doesn't satisfy phi? That is the definition of M satisfies negation phi. Yes, so therefore exactly one of M satisfies phi and M satisfies negation phi holds. Therefore exactly one of phi or negation phi belongs to theory of M. What does that mean? I mean, theory of M is deductively closed, right? So, I mean, essentially here we have, I mean, maybe I should write it here in red. So, phi belongs to theory of M. When does it belong? If and only if it's a logical consequence, right? So, therefore, exactly one of course, both of them can't be, because theory of M is satisfiable. It's a theory. When did I say it is if and only if? Huh?
No, why is it if and, like, why does phi belong to theory of M
if and only if it's a logical consequence? Because it's deductively closed. If you remember the proof of completeness theorem, yeah, we proved claim 1. What was claim 1? It is a maximal theory, and then after claim 2, that was step 1, that it is a maximal theory, and step 2 claim 1 was that it is deductively closed. Yeah, so theory of M is deductively closed. So therefore exactly one of M has phi as a logical, theory of M has phi as a logical consequence, or theory of M has negation phi as a logical consequence. Can both of them happen simultaneously? No, because it is satisfiable. Yeah, if phi and negation phi are both logical consequences, then their conjunction will be a logical consequence. Correct? Okay, so that cannot happen. We cannot prove a contradiction by the theory of a structure, because then that contradiction is true in the structure. That's impossible. Okay, so that's all. Yeah, I mean, here we are using that theory of M is deductively closed. Okay, let's proceed. Show that the following are equivalent. Gamma is a theory. Yeah, gamma is complete theory, and any two structures for any two models of gamma are elementarily equivalent. Yeah, this is the symbol for elementary equivalence. So let us recall that M is elementarily equivalent. Yeah, elementary equivalence. Let me write it if you have forgotten. If, what is the definition? Their theories are equal. Theory of M is equal to theory of M dash. So this is a quite interesting statement. Yeah, gamma is complete if and only if. Now gamma is complete is entirely dependent upon the symbol. Yeah, the double turnstile symbol. You are starting with an arbitrary sentence and then gamma will make a decision for it. Either phi is a logical consequence or negation phi is a logical consequence. On the other hand, any two structures being elementarily equivalent, any two models of that theory being elementarily equivalent, that's entirely semantic thing. I mean, I understand that even double turnstile is a semantic consequence relation, but this thing is, you are just checking this. Yeah, and we'll see some examples of complete theories in this tutorial, and you will see what I mean here. So, how do you prove 1 implies 2? Any ideas? If gamma is complete, then what happens? You start with any, so 1 implies 2. Oops. So suppose gamma is complete. And M and M prime are models of gamma. Okay, if this happens, then what can you conclude? Like M and M prime are models of gamma. So what can you say about theory of M and gamma? What is the relationship between them? Gamma is a subset of this, and but gamma is complete. Okay, gamma is complete. So it makes a decision. So let gamma prime be defined to be all those sentences such that gamma entails theta. So this is the deductive closure. Yeah. I mean, even though I am using the word deductive closure, I don't really mean a syntactic thing. Yeah, deduction has to do with the single turnstile relation. But we are not talking about that, because in predicate logic we decided we won't talk about proof systems at all. Okay, so what can you say about theory of M and gamma prime? Then if theta belongs to gamma prime and M is a model of gamma, then what can you say? Then M also satisfies theta. Yeah, because theta is a logical consequence of gamma. So just by definition, so therefore, what can we conclude? That gamma prime is also contained inside theory of M. Yeah, I mean all the definitions are here. Just convince yourself that gamma prime, the collection of all logical consequences of gamma, those are also true in M. True in M is a subset of theory of M. Okay. Any questions so far? Fine. Let's proceed now. So gamma prime now is not only complete but it's also deductively closed. What did we show here? Theory of M is complete and deductively closed. So complete and deductively closed, what does that mean? If you add anything which is not in there, then it will explode. Then it becomes everything. Yeah, so it can also prove contradictions. So obviously that cannot happen, both of them. Now since both gamma prime and theory of M are complete and deductively closed, okay, what can we say? Gamma prime and theory of M have to be equal. Okay, so gamma prime was the deductive closure of gamma, and we have shown for any model M, theory of M is equal to gamma prime. So in particular, so therefore if M and M prime are models of gamma, then theory of M is equal to gamma prime equal to theory of M prime. So in other words, M and M prime are elementarily equivalent. Okay, so this is what we wanted to prove. It looks long, but the idea is very simple. I mean, you don't really have to write this. You just have to start with this deductive closure and then proceed. Yeah, we are discussing the ideas here. Okay, what about 2 implies 1? The proof is actually hidden in these steps itself. If any two structures, so whenever you are given a theory, yeah, you can always take its deductive closure. So for example, if I am given the theory of groups, then the deductive closure of the theory of groups, which is just 3 axioms, associativity, identity and inverses. So only 3 axioms, that is a theory. But if I am given a theory, then I can always take its deductive closure, and those will be all the sentences which are true in all the groups. That is the deductive closure. Now, once you know that it is complete, I mean, how do you know something is complete? Well, the deductive closure must contain exactly half of the elements, half of the sentences. That's all is required. And via, like, trace these steps back, you will get it. Okay, I'm not writing it out. Instead, I would like to show you some example of a complete theory. So let us go here. So if you remember, there was a quiz question, just a 1-mark question. Write down that a particular structure has at least 100 elements. Yes? Well, the performance of the class was poor on that question, but maybe those who got it right can tell me what should be this answer. How can you write down that the theory, this is the theory of infinite sets. When do you say that a structure is infinite? I mean, this is more like a philosophy question. Yeah. When do you say that a structure has only 4 elements? That's our second question. Maybe that's easier to answer. Yes? It has only 4 elements?
There exist 4 elements and there do not exist 5 elements.
Yes, there exist 4 elements. And how do you express that there are 4 elements in a structure? There exists W1, W2, W3, W4 such that
Negation of Wi equals
Wi and Wj are not equal. Okay? And then you say that there do not exist 5 elements. So let us write this down. Yeah. So there exist W1, W2, W3, W4 such that Wi is not equal to Wj for any I and j between 1, 2, 3, 4 but distinct. Okay, so this is the sentence which says that there are 4 elements which are distinct. So what is the interpretation of this? We actually, will prefer to call it sigma bigger equal 4. Yeah, sigma is a sentence which says that there are at least 4 elements. And then how do you say that there are exactly 4 elements? It must contain at least 4 elements and it must not contain more than right. So sigma 4, we can say that the same thing happens. Yeah, there exists W1, W2 up to W4 such that conjunction of 1 less equal I less than j less equal 4 such that negation Wi equal to Wj and okay, this thing holds, and on top of that for all W, one of this is true. Right? What am I saying? That every element is equal to one of these W1, W2, W3, W4 interpretations. So one of them is true. It can't be 2 of them simultaneously because of the first condition. So at least one of them is true. You understand this? There is obviously an easier way to write this by saying that sigma bigger equal 4 holds, conjunction negation sigma bigger equal 5. Right? But they are logically equivalent. Yeah, so this is also logically equivalent to sigma bigger equal 4 and negation sigma bigger equal 5. So there are at least 4 elements, but there are no 5 elements. Okay, so this is gamma 4. Gamma 4 is the theory which says that there are exactly 4 elements. Now the question is this complete? Is this theory complete? So what is our language? L sets. What does it consist of? Nothing. Yeah, it's empty language, just equality. Okay, so suppose, what do you have to show? For 2 different sets containing 4 elements, can you really say 2 very different things? Any 2 sets with 4 elements are in bijection with each other. So therefore, whatever you can say here via that bijection, you can transfer over here. So actually, only containing 4 elements is sufficient to determine the truth of every single sentence. Okay, I am not giving you a proof of this, but are you convinced that this is true? If, okay, yeah, I mean, think about this. If I say a theory has a 4-element model, yeah, I mean a theory in L sets, in the language L sets, empty language, has a 4-element model, then the statement that it has 4 elements is true, is a logical consequence of that theory. So it cannot contain 5 elements, it cannot contain 3 elements, it cannot contain infinitely many elements. So for every model, it must contain exactly 4 elements. And because any 2 sets with 4 elements are in bijection with each other, which means they are isomorphic. Yeah, bijections are isomorphisms, structure isomorphisms in L sets, because there is no structure to preserve. So, because any 2 structures are actually isomorphic, they are also elementarily equivalent. And therefore, by whatever we just proved, 2 implies 1, we will get that the theory of sets containing 4 elements is complete. Do you understand what's going on? Yeah? And if you understand this, then perhaps you should try to answer this question. What is the theory which says that there are infinitely many elements? Any ideas? Can you write down a single sentence which says that there are infinitely many elements?
We can first say that there is one element exists W1, and then we can have another sentence like for value, the infinite conjunction idea. It is not.
Can we use infinite conjunctions? No, we cannot use. Yeah, our logic is L omega omega, which means we can only use finite conjunctions, finite disjunctions, and finite quantification. So any other attempt at saying that there are infinitely many elements in one sentence, if you can write down finitely many sentences for a theory, then you say it is finitely axiomatizable. Theory of groups is finitely axiomatizable. Theory of rings is finitely axiomatizable. Theory of vector spaces is finitely axiomatizable in an appropriate language. Yeah, I mean that's that one is tricky. But is the theory of infinite sets finitely axiomatizable? Just share your ideas. Just saying no is not enough. Then give me infinite collection of sentences which show this. What if I add sigma bigger equal n for each n? Then every model of this theory must have at least n elements for every n, which means it must have infinitely many elements. Yeah, that's the answer. So what is gamma in sets? You add so many sentences. Okay. Now, what do you think? That is this complete I will answer this question better in the next week. Okay, but the answer to that is complete. Okay, thanks to wash-what test. Okay, now you are reading an L, but the pronunciation of this Polish alpha letter is W. Okay, so this is wash-what test. Okay, it says this: if a theory gamma has no finite models and for some infinite cardinal kappa there is only one model of gamma up to isomorphism, then gamma is complete. Now, gamma inf set, does it have a finite model? No. And let's say countable cardinality, aleph naught. For aleph naught cardinality, how many models of gamma inf set are there up to isomorphism, means up to bijection? Only one. Yeah, because all countable sets are in bijection with each other. So therefore, by this test, you conclude that it is complete. Yeah, so this particular statement, there is only one model up to of gamma of cardinality kappa. This particular statement is known as kappa categoricity. Next week I will prove this. Yeah, but for now you just have to accept. Okay. Any questions? Then let's move forward. Are the following pairs of structures elementarily equivalent? The ordered set of natural numbers and ordered set of rational numbers. Are they elementarily equivalent? No. Sriram, why?
For every element there's an element smaller than it is true in P.
Right. So does not have a minimum is a sentence which is true in the second structure but not in the first structure. Yeah. So does not have a minimum. You can write down this sentence. Yeah, what is the sentence? For all W1, there exists a W2 such that R W2 W1. So this is true in but not true in N. What about the second one, natural numbers with addition and rational numbers with addition? No, yes, good.
You can write like 0, you can single out 0 in N plus, but you can't do it in P plus.
How can you single out 0 in N plus?
Like creating less than, using like there exists a number such that.
By creating less than, but I think you can also single out 0 in Q plus by saying it's the additive identity. Yes, that's not working out then. How about this? That the number can be divided by 2. I mean, it is twice something. It is something plus something. Every rational number can be divided by 2, but not every natural number can be divided by 2. Yeah, I mean this sentence, that for all W1 there exists a W2 such that f of W2 is equal to W1. This particular sentence is true here and false here. Okay, let us go to the third one, rationals and real numbers as orders. They are elementarily equivalent, okay, but right now you do not have the tools to say so. The answer to that is yes, yeah, because gamma DLO unbounded. DLO, you know, dense linear orders, and unbounded, it doesn't have a minimum, it doesn't have a maximum. This is complete. Okay, so this is complete, and therefore any two models of them are elementarily equivalent. We just showed that. And we'll see the answer to this next week. We'll use wash-what test to conclude this, that why this is complete. Okay, the last one, the ring of rationals and the ring of reals. No? Yes? Tell me why.
We can, like, if we can isolate positive numbers, we can do the square.
Positive numbers, okay.
We can then do the thing that every positive real number has a square root.
Very good. Every positive number has a square root. Which one in particular? 2, right. 2 has a square root in real numbers. 2 doesn't have a square root in rational numbers. But how do we write 2? 1 plus 1. So basically there exists a W such that W square is equal to, I mean this is FG, F of E comma E. Yeah, this is CE, E comma E. This is true here, but false here. So that's all you have to do. Yeah, I mean this is a very simple type of question. If you want to show two structures are not elementarily equivalent, you have to find out a property which is true in one structure but not in another, and then you have to express it using a formula. Yeah, that part is essential. Let's proceed. Okay, PCFN. CF stands for finite cofinite. Yeah. So finite and cofinite. Is this a sub-algebra for following structures? So sub-algebra, okay, I mean this is perhaps a very complicated way to say, but what it is asking you to do is prove that every finite subset is definable. Okay, so in natural numbers with less than, I mean all of them are with natural numbers. Okay, so with less than, how can you define singleton 0, for example? What is the property of 0 with respect to order in natural numbers? It's the minimum. Yes, so you can define 0. Please tell me the formula. Loudly, Sujal. There does not exist. So there does not exist any W such that RWX. Yeah, so this particular formula will single out 0. Yeah, so this is true only at, if this is my phi of x, then I should say that phi of n is equal to singleton 0. Okay, how about showing that singleton 1 is definable? What is singleton 1? It is the immediate successor of 0 with respect to less than. So only 0 is smaller than that, but nothing else is smaller than that. And now because 0 is definable, we can write down that sentence. Yeah, so for all W, RWX implies that phi of W holds, where phi is the formula above. So if W is smaller than X, then W is 0. This describes 1. Then similarly you can write down what describes 2. You can describe what is 1 million. Yeah, because there are only so many things less than that. It's still a finite formula. And then how do you say that it, let's say 1, 2, 4 is definable? You say that the element is either 1, disjunction it is 2, or it is 4. So every finite set is definable, and therefore every finite subset is definable, and just put a negation on top of that, then every cofinite subset is also definable. Any questions? Cofinite. Cofinite is complement of finite. So you just say negation of this formula. If I can define 1, 2, 4 as a definable subset, then I just put a negation, then it says that everything apart from 1 to 4 is definable. Okay. Now natural numbers with shift operator. Shift operator. So, is 0 definable? Yes. How? Yes. So negation W such that S of, maybe I should use this F. Yeah, F of W is equal to X. Yeah, this defines 0. Then how do you define 1? It is the successor of 0. And that way you can define every single element, every single singleton, and therefore you can define every finite set and hence cofinite set. Okay, what about addition? Yes? You can write less than using addition. That's a good way to go. And also you can express that it is identity. And how do you express 1? Using addition. How do you express addition, less than using addition?
There exists something that's it.
So x is less than y if and only if y is equal to w plus x for some w, which is not 0. So I think you can express all these things in this language, and therefore every finite set is definable, and therefore every cofinite set is also definable. So actually the more technical term for this is less than is definable in this structure. And therefore whatever you can do here, you can do here. Okay, so less than is definable by, this formula. So x less than y if and only if for x is not equal to y, and there exists a W such that, I mean, if this is my f, then f of Wx is equal to y. This defines less than, and therefore everything that you can do with less than you can do here. What about multiplication? Can you define less than using multiplication? No. Okay, but proving that something is not definable is actually quite hard. You can define singleton 1 here, because singleton 1 is the identity. Then you can define 0 here. Why? Because 0 kills everything with respect to multiplication. Yeah, so anything multiplied by 0 is 0. That's why you can define 0. So you can define 0 and 1, but can you define 2? Okay, so not all finite subsets are definable. Yeah, so here I am not giving you a proof, but because proving that something is not definable is actually hard. Okay, let's go to the next problem. Prove or disprove. I think we have done first one in the class. Yeah, while proving some logical equivalences. Is it true or false? Tell me. For all W1 there is a W2. False. Give me a structure where left hand side is true but right hand side is false. The second one says, so if you interpret it as less than, then the first statement says that there is no upper bound. Okay, good. There is no maximum. And in a linear order. What about the second one? What does it say?
There is a maximum.
There is a maximum. So obviously that can't be true. Yeah, you take it in natural numbers with less than as the interpretation, and this is true, that is not true. But I mean, you should look at model answers and know how to write this. Yeah, because it's not a test of whether you can find this structure, it's also about whether you can write about it. Unravel the definition of semantic turnstile. What about the second one? Is it true or false? So there is a W which makes the conjunction true. So therefore, it makes both of them individually true. Okay, how do you prove this? You should start with, so there is also X bar here. So let M be any structure and A bar be in M. Suppose M satisfies LHS at A bar, and then you continue. Okay, you write down the English meaning of this, then from that you conclude that the English meaning of the right hand side is also true. Right? That's how you should proceed for such types of questions. Let us go here. Find the formula in the pre-next normal form, which is logically equivalent to this thing. How do you do something like this? We already have some standard logical equivalences. Which bracket will you try to attack first? Pre-next normal form means all the quantifiers are in the beginning. So you should beginning means always on the outside. So you should always start from the inside and try to bring every quantifier outside. So what about this? There exists a W2 such that PW2 conjunction are W1, W2. I hope I have written the brackets correctly. Yeah, 1, 2, 3. Yes. I mean, obviously there is this extra pair of brackets as well. Yes, tell me. How do you take this thing out? This there exists. For all W1, and then inside what will it become? So this is logically equivalent to for all W1, I should take it out from, so see, this is like, this is the green bracket, then there is one thing outside, so I should take it out from this blue one, the inner one. And no, but that is not sufficient either. I think I have written one extra pair of, no, this is not the correct one. This is the correct one. Right, and then I am supposed to bring it out. So for all W1, for all W2, what should I write inside? Keep it the same, right? PW2 conjunction RW1, W2. There should be a parenthesis. And I think we are done by putting this. Okay, so the process here is simple. You just have to use this logical equivalence sequentially. Maybe I should do one more. Yeah, the second problem is this. For all W R W W implies there exists W R W W. How do you write it in pre-next normal form? The first problem is that the scope of different variables is different. So you should change one variable to something else. So let's say we are changing this one. Okay, then we can take out this, there exists. How can you take it out? As it is, right? And this for all you will take it out as, okay, so with one more step in between, you will get that there exists W1, there exists W, such that RW1, W2, W1, W1 implies RWW, and that's all. I mean, actually this is a tautology. Yeah, because if the first one fails, then the implication is true, and if the first one is true, then so is the second one, so therefore the implication is true. Okay, so let us stop here. Well, let us do one more question, that is question number 5. So that is, I from rational numbers to real numbers in the language of +.01. This is your language. Can you show that the inclusion map is a structure homomorphism? Do you remember the definition of a structure homomorphism? It must preserve addition, it must preserve multiplication, and 0 and 1. So which is quite simple here. Oh, sorry, there is also less than. What do you do with less than? It also must preserve order. Okay. Now the question is, does there exist any other homomorphism between these two. Inclusion is definitely a homomorphism. This is like ordered ring. Yeah, ordered ring homomorphism. So 0 goes to 0, 1 goes to 1. Can there exist anything else which preserves order and addition and multiplication? No. Why?
If 0 goes to 0 and 1 goes to 1, Q is already like embedded.
Exactly. If 0 goes to 0, 1 goes to 1, then where will half go? Half plus half is 1. So therefore, if it is a homomorphism, it must preserve addition. So therefore, if phi is a homomorphism, if alpha is a homomorphism, alpha from Q to R is homomorphism, then alpha of half plus half is equal to alpha of 1, and this is equal to 1, and this is what? Alpha of half plus alpha of half, which is 2 times alpha of half. Well, therefore alpha of half is half. So therefore this way you can show that all rational numbers are preserved. So there is no other homomorphism possible. The rest of the questions are easy, you can do them. Dependency theorem, you should try to write it down. Yeah, that's a good exercise to understand semantics. Let's stop here.